So, did you find out anything about the right triangles?
Actually, I did. Not too much though. I only found out about the similarity between right triangles.
We need that too.
Okay, so do you know what the geometric mean is? Let's just say that b, c, and x are positive numbered variables. X would be the geometric mean when b over x equals x over c. Get it?
Oh, I remember this. I've heard it before. There's even a theorem. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. It's trying to explain that if there is an altitude to the hypotenuse of a right triangle, the two triangles that the altitude had created in the original, bigger one are all similar to each other. I don't remember the corollaries to this theorem though.
I can tell you. Corollary 1 is, when the altitude is drawn to the hypotenuse of a right triangle, the length of the altitude is the geometric mean between the segments of the hypotenuse.
Oh, so when you draw an altitude, you divide the hypotenuse into two segments, B and C for example. Right? And you can find the length of the altitude by using it as the geometric mean, x. So B over x equals x over c.
You got it. Corollary 2 is, when the altitude is drawn to the hypotenuse of a right triangle, each leg is the geometric mean between the hypotenuse and the segment of the hypotenuse that is adjacent to that leg. For example, let's take a leg from the original right triangle and call it leg x. The altitude divides hypotenuse h into two segments, B and C. B is adjacent to leg x. If leg x is the geometric mean between the adjacent segment, B, and the hypotenuse, h, b over x equals x over c.
Oh, okay. Next, your mission is to bring me information about the well-known Pythagorean theorem. Go. You did well.
That in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the legs. We can find x by squaring 9 and 12 and adding them, and then finding the square root of that number. We see that x is 25. We can further use the converse of the Pythagorean theorem to see if a triangle is right, obtuse, or acute. If angle C is the angle opposite the hypotenuse, C, and the legs are named A and B, if c squared is equal to a squared plus b squared, then angle C is 90 degrees and the triangle is right. If c squared is less than a squared plus b squared, then angle C is less than 90 degrees and the triangle is acute. If c squared is bigger than a squared plus b squared, then angle C is bigger than 90 degrees and the triangle is obtuse. We can use the Pythagorean theorem and its converse to figure out these examples.
This lesson is on special right triangles. And to begin with, there are two types of special right triangles, the 45-45-90 triangle and the 30-60-90 triangle. The 45-45-90 triangle theorem states that the hypotenuse is rad 2 times as long as the leg. And we could actually prove this theorem by solving for h in terms of a. Just like this. This is the Pythagorean theorem. And you plug in the leg, which is A, into right here, and H, which is the hypotenuse, into C. So it turns out to be 2a, rad 2a squared is equal to h squared, and it actually turns out that a rad 2 is equal to h, so just like the theorem stated. Secondly, we have the 30-60-90 triangle, and the theorem states that the hypotenuse is twice as long as the shorter leg, and the longer leg is rad 3 times as long as the shorter leg.
Sections 8.5, 8.6, and 8.7 deal with trigonometry and right triangles. Section 8.5 is all about tangent ratio. And what the tangent ratio is if you take angle A or B in this case, and you take the opposite side of that angle, so for angle A that would be side BC, and then you take the measure of that and put that over the measure of the adjacent side, or side AC, you'll get a ratio known as the tangent. And using this, you can discover either the measure of angle A, or if you know the measure of angle A and only one of the sides, you can discover the length of the other side. In section 8.6, we will be learning about the sine and cosine ratio. The sine ratio is when you take either angle A or angle B, and you take the measure of the adjacent angle and the measure of the hypotenuse, and you put that into a fraction where sine A equals adjacent over hypotenuse. So for angle A, that would be the measure of AC over the measure of AB. And you could use this to determine either the measure of angle A, or if you already know that, you could use that to determine one of the lengths of the sides, either the hypotenuse or the adjacent side. The cosine ratio of angle A is the measure of BC, or the opposite side, over the measure of AB, or the hypotenuse. This can be used in the same way that you use the tangent and sine ratio, where you can find the measure of angle A if you don't know that, or you could find the measure of one of those sides, the hypotenuse or the opposite side. In section 8.7, we'll be learning about real-life uses of right triangle trigonometry. In this picture, you can see that about 8 feet up a wall is a security camera mounted such that is aimed at an angle of depression at about 5 degrees. And what this basically is how much lower than the horizon line, so the horizontal line above it is aiming. So if you were to be looking down, that would be an angle of depression. Angle of elevation, on the other hand, is if you were to be looking up. These can be used to measure distances or angles. So if you know the distance between the base of the wall and where the person is standing, then you could find the angle of depression. But since we already know that the angle of depression is about 5 degrees, we could use this to find out the length of x. Since we know that the camera is about 8 feet above the ground and that the angle of depression is 5 degrees, we know that the angle next to the camera is 85 degrees and the angle next to the boy is 5 degrees. We could use the sine, cosine, or tangent ratios to find the length of side x, which we will do in the next example.